Baik, Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Luthfi Ardien, and right now I'm gonna do an evaluation about how did I do on my quiz of mechanical fluids at last Tuesday with DAI. So the first question is about nature. What is nature based on my perspective? So for me, nature is an environment that is not intervened by any third parties such as human living beings. So it's purely uh, an environment purely only from God without our intervention and stuff like that. So nature I think consists of all living organisms such as also landscapes, ecosystems, and other processes are occurring on Earth. Earth. Nature exists everywhere on Earth, from the sea, the land, and other places on Earth. It's been evolving since the very beginning to the present now due to interaction of all living things on Earth. Not the living things, not just all the living things. The non-living things also interact with each other that made the Earth evolve around the years, which makes it very different from the very beginning it was created. How it operates is just interaction between all things and mostly time. This is the key of evolving of the Earth, which is time. With time, every single second, every single minute, every single hour, etc., the world and its nature has been evolving. For example, the natural phenomenon that we know on living beings, such as photosynthesis, Preterian decomposition, and natural selection. These things make up the evolution of nature for the past this hundreds of millions of years the earth has been alive. In summary, nature is something that at first has not been interacted by living beings, which was gifted by God, and the evolution that all living beings has done to the nature made it change. So, in the diagram I wrote here, nature in the beginning has not been interacted by other living beings, so it's purely from God. In the present day now, has been evolving and it has been changed from the way it looked from the very beginning due to all the things that interact on Earth with time as it goes on. Second, I'm gonna explain about compressible flows. So I'm gonna divide this into the concept of DAI 5, which is four concepts. Intention. This is conscious thinking. I I join it with intention because conscious thinking and intention go well together. And then also initial thinking, idealization, instructions. So in the conscious thinking and the intention I did to analyze about compressible flow is I hereby right to evaluate about the compressible flow based on the information from the internet, books, and other medias to educate myself because education is one of the fundamentals of life as a worshipper of God for me. Initial thinking. Before we get into the details about compressible flow fundamentals, let's start with the definition of what is compressible flow. So basically, compressible flow, if we study before about incompressible flow, basically it's just a fluid that when it flows over time, the density doesn't change, which is completely different to compressible flow. Compressible flow is something when a fluid flows, the density changes over time. This usually is the most cases when gas flows over immersed bodies, such as when a plane is flying through the air, the gas around it, or we call the air around it, flows into the body like immersing the body in it. Like the flow It just over time density always changes. So compared to incompressible flow, incompressible flows assume the fluid's density remains constant throughout the flow, whereas compressible flow assumes the fluid density remains density changes throughout the flow. In terms of application, compressible flow is for like high-speed aerodynamics, jet engines. So compressible flow is like something that is heavy duty, like something moving fast, rockets, planes, cars, motorcycles, and other stuff like that. For incompressible flow, it's something like low speed fluid flows such as hydrodynamics, pipe flow, all that kind of stuff, pipe flow, open channel flow, which in rivers like water flowing, those are incompressible flow. Because the water cannot change water is too hard to like change in density, so it remains stable all the time, density of the water. So for idealization and instruction, I'm gonna dive down into the details about uh what is compressible flow. I just said the definition. Now I'm gonna get into the details on how we can actually tell if the flow is incompressible or compressible. So we can tell if the flow is compressible or incompressible by looking at its Mach number of the flow. So what is Mach number? Mach number is a unitless quantity in fluid dynamics that tells you how fast something is moving. Well, actually, it's not. It's not. It doesn't tell you how fast something is moving. It actually tells you how compressed the object is due to the air flowing so fast to the bodies, like in immersing. It creates a pressure so high the object is compressing due to the air. So it can be defined mathematically as ma, which is Mach, equals to v divided by c. So v, this is the local flow velocity of the object. So for example, a plane moving at 1000 miles per hour. That is the local flow velocity. As for c, this is the speed of sound. Basically, the speed of sound is around 343 meters per second. So, a count benchmark, if we want to determine if the flow is incompressible or compressible, is actually when the Mach number of the flow is 0.3 or more. At this point, the flow is we can say the flow is compressible. If it's below 0.3, it defines as an incompressible flow. Because when the Mach number is at 0.3 or more, the changes in density becomes more significant and it's considered a compressible flow. So there's this correlation between ideal gases and with compressible flow, so we can determine its entropy change with this kind of equation. So basically, this is just a change in entropy, and this is the constant for particular ideal gas. So it basically depends on the ideal gas we are talking about, and at this point, T2 and T1 is just a change of temperature as well, and density is this ρ1 and ρ2 is just also a change in density. So we can determine the compressible flow by looking at its Mach number, based on its Mach number. So first of all, there is one. We can determine it if it's below 0.3 in Mach number. It's definitely in an incompressible flow. But if it's starting to be above or equal to 0.3, we can call it a subsonic flow. And this is the flow where the flow is starting to get to the compressibility part. And we can get even higher to the interval around the range of 1 to, I guess, like around 2 or 3. We can call it a transient flow. And at that point, if we go even higher, we are getting to the point where it's until Mach 5, which is supersonic flow. This is basically common around jet planes and military aircrafts. They usually go around the speed of supersonic flow, but they can actually go higher than that. They can actually go to the next phase, which is hypersonic flow, which is around 5 Mach until a little bit over 10 Mach. And actually, this is, I forgot what it's called at this part. Actually wrote it wrong. It's not hypersonic flow, but yeah, it's higher than hypersonic flow. So there's this diagram which changes based on the kinematics on the plane in motion. So as an object accelerates from a subsonic towards supersonic speed in a gas, different types of wave occurs. I want to illustrate this first. So basically, this circle right here defines the object when it's stationary. So as you can see, the circles line very tidy with each other. But at a point where the plane starts to go in motion and go really fast, like about to Mach 1, 0.8, and other kind of Mach numbers. So I'm gonna compare right now. So this is first the stationary, where it's completely not moving. So and when we get to this point, it starts to move a little bit. It is in the subsonic and sonic flow, where the Mach number is below 1 but it's above 0. So as you can see, the circle is like moving to the left. When we reach Mach equals 1, the circle on the center really touches the boundary of the outer circle in the left. But here's the interesting part. When we get to the Mach greater than 1, it becomes very distorted, like the circles create like a sort of row that if we draw like a little bit of line right here, it forms some kind of angle. Now this angle is called Mach angle. When this occurs, the locus of this wave trailing behind the point creates an angle known as the Mach angle or Mach wave angle. It can be mathematically defined as sin of the Mach angle. I'm gonna define this Mach angle as alpha equals to C per V. Basically, it's just a reverse part of the Mach number, which you can define also as 1 per Mach number, as you can see right here. So we can define the Mach angle with this equation right here. On that note, there is something interesting about compressible flow. So compressible flow, we can analogically compare it to open channel flow. The propagation of weak pressure impulses or sound waves in compressible flow can be considered comparable to the movement of small amplitude waves on the surface of an open channel flow. In each case, two-dimensional flow and open channel flow, the influence of flow velocity of wave pattern is similar. When the flow velocity is less than the wave speed, the wave fronts can move upstream to where the source and the flow is sonic. Which is sonic is like a type of flow that is in the compressible flow section, or we can divide as critical, which is the in the open channel flow section type flow. But when the velocity is greater than the wave speed, the flow is supersonic, which is in the compressible flow section, or supercritical in the open channel flow section. Now this is like the interesting part. Like if the Mach number is super, then the float number is gonna be also super. Like supersonic, supercritical, sonic, critical, subsonic, subcritical. It's very interesting. In compressible flows, there it has a meaningful variable which is Mach number. In an open channel flow, there is a dimensionless number which also indicates its criticalness, which is float number. Which the equation is basically Fr equals to VOC divided by root of Z times Y. So basically, we can actually substitute this into COC, which is like the small amplitude wave function. Function on the surface of an open channel flow. Basically, it's like really the same as Mach number, but if let's see. So this is we substitute this as COC, and we get this correlation right here. So Fr is equals to VOC divided by COC, as where Mach number is V divided by C. If you look at it, it's very similar. Am I right? It's very similar, but its application is different. But is what it indicates is actually kind of the same, I guess. But how it defines it is pretty different. But and actually not that different. But the application for it is different. Like we cannot actually use Mach number on open channel flows, and we can actually get the float number on compressible flow. It has in its own functions, but in the end it's actually similar. So this is the application of compressible flow that I actually just think of it. Like we can see there's a jet plane moving at 1,000 speed. I assume this because an average jet plane usually goes at 1,000 miles per hour, which is 447.04 meters per second, which creating a shockwave as it travels. When a jet plane creates a shockwave, it already reaches more than Mach 1. Does the air flowing around the plane considered compressible flow? I don't know. If it does, how big is the Mach angle created by waves traveling? Well, we can solve this first by utilizing our intention. So my intention of doing this is I'm doing this to test my evaluation of the knowledge for compressible flow I gained for myself and mostly forgot. My initial thinking is if we want to determine a compressible flow, we can use something like a dimensionless unit. For compressible flow, what we can use? Correct, Mach number. So we can get to the equation right now. Mach number is equals to V divided by C. So it already has been defined what is the local velocity of the plane, which is 447.04 meters per second, but I just put it 447 right here. I don't know why, but I didn't put the 0.04, but it's almost the same, yeah. So the speed of sound is actually 343 meters per second in definition. So we just put it there, and then we divide it. It equals to 1.3032, which is more than 1, which we can call that a supersonic flow. We get the Mach number is 1.3032, which is above 0.2. If it's above 0.2, it's considered a compressible flow. But it also is above 1, which the type of the compressible flow is supersonic. This means we can get the Mach angle for it. How to define it? we can use the good old equation sin of the Mach angle equals to 1.ma. We already get the ma, which is 1.302. Actually, I type it wrong, but yeah, it's we can put the Mach number here and put the Mach number right here. We can get the if we can use this and then move it and then we can use the arctan method, arcsin method. We can get the Mach angle is equals to 50.179 degrees, which we can define right here at this part right here, the angle it created by the movement of the plane with the wave of the plane, which is 50.179 degrees. So we can conclude that it is compressible flow, a supersonic flow with a Mach angle of 50.179 degrees. I think that's all from me for the evaluation of quiz MacFlow with Mr. DAI. Thank you so much for watching this. If I made a mistake when I'm presenting, please forgive me, and I'll be heading out. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.